Good day, everyone. So, before we start our topic, we will just first introduce ourselves. By the way, I am Nicole Jamora,
I am Miichael Monsida.
and we are from Group 12. So, first topic is the solar thermochemical energy conversion. So, what is solar thermochemical energy conversion? Solar thermochemical energy conversion, it drives chemical reactions with concentrated solar energy. It transforms solar energy into chemical energy that can be stored, such as carbon monoxide and hydrogen. It creates clean, transportable fuels through high-temperature reduced cycles. It allows solar energy to be stored and transported over long distances. So, solar thermochemical energy it turns sunlight, then high heat, to chemical fuel. So it is important because fuel can be used even when sunlight is unavailable. So next, we're here the process of solar thermochemical energy. So the first one is the redox cycle, solar concentration, fuel production, energy storage. So the first process of the solar thermochemical energy is the redox cycle. Redox cycle is a metal oxide that are used in a recurring cycle of reduction and oxidation. It transforms solar heat into chemical energy that can be stored in fuels. A redox cycle has two stages, the reduction step and the oxidation step. So, a redox cycle is the repeated chemical reaction cycles. So, it absorbs solar heat or reduction and releases fuel or oxidation. So there are two stages of redox cycle. So the first one is the reduction step, then the next is the oxidation step. So reduction step is the process of the solar heat raises materials. Example is the metal oxide to very high temperatures. Material breaks down and releases oxygen. This creates a chemical reactive reduced state. The temperature range of the reduction step is often 1400 degrees Celsius or higher. So the material becomes reduced by losing oxygen. The next is the oxidation step. So it reduced materials reacts with water or H2O or carbon dioxide or CO2. It produces hydrogen or carbon monoxide. It regenerates the original oxide material to restarting the cycle. So in the oxidation step, the reduced material reacts with water or carbon dioxide to produce hydrogen or carbon monoxide. After this, the material returns to its original states and the cycle restarts. So the oxide is regenerated for the next cycle. So next is the solar concentration. Solar concentration is it supplies the intense heat required for redox processes. It focuses sunlight to produce temperatures above 1400 degrees Celsius. So to reach the high temperatures needed, sunlight must be concentrated. Solar towers, heliostat fields, and parabolic mirrors focus sunlight to create extremely high heat for the reactions. CSP or concentrated solar power technologies focus sunlight to produce 1000 to 1400 degrees Celsius. Next, the fuel production. So in this stage, solar heat is transformed into chemical fuels. Water and CO2 become hydrogen, carbon monoxide, or syngas. These fuels can later be processed into methanol or synthetic liquids. So fuel production describes the process of using solar energy to convert raw feedstocks such as carbon dioxide or water into usable chemical fuels. So it is the process by which solar energy is stored in chemical bonds that transform into fuels that can be used such as hydrogen, carbon monoxide, or syngas. So this can be processed into liquid fuels, synthetic hydrocarbons, methanol, or other high-value chemicals. So the main input is the hydrogen, carbon monoxide, and syngas. So this can be refined into liquid fuels. And the last process of the solar thermochemical energy is the energy storage. So energy storage is chemical bonds store solar energy. Unlike electricity, fuels can travel great distances. It makes it possible to use solar energy even in isolated locations or at night. It assists in overcoming intermittency's limitation. So unlike electricity, chemical fuels can be stored for long periods and transported easily. This allows solar energy to be used at night, during cloudy days or in remote areas. Chemical fuels is equals to long-term energy storage, solves the intermittency problem of solar energy. So next is the advantages and challenges of solar thermochemical energy. So the advantages is the first one is they utilizes plentiful feedstocks such as carbon dioxide and water. And next is the possibility of increased efficiency in contrast to alternative solar to fuel techniques. And fuels are easy to transport and store. So, the pros or the advantages is the abundant resources, efficient and goods storage. However, the challenges is the rapid temperature changes and fluctuating solar flux must be managed. Next is the extremely high heat levels are necessary for reactions. Then the reactors powered by solar energy must endure extreme heat, and reduced materials must endure several cycles without deteriorating. So, it is the high heat, material stress, or the engineering difficulty. So, this will be the end of my topic, which is the solar thermochemical energy conversion. And the next topic will be discussed by Miichael Monsida.
Good day everyone, by the way I am Miichael Monsida and this brings us to the second half of our presentation. Hydrogen energy conversion systems. What is a hydrogen energy conversion system? A hydrogen energy conversion system is a framework that transforms hydrogen into a stable energy. The key processes include electrolysis for production, fuel cells for electricity generations, and combustion for heat and power. When hydrogen is produced using renewable energy, what we call green hydrogen, it becomes a versatile and completely clean energy carrier. This slide provides a simple overview of the three main processes we will discuss. First, electrolysis to make hydrogen, fuel cells to use it for electricity, and combustion as a direct use method. The first main process is electrolysis. This is how we produce green hydrogen. It is used electricity ideally from solar PV, wind, or hydropower to split water into hydrogen and oxygen. You can think of it as a fuel cell running in reverse. The hydrogen produced can be stored and later converted into electricity, making it a key solution for long-term energy storage. The second process is fuel cells. This is a clean and efficient way to use stored hydrogen through an electrochemical reaction. Fuel cells combine hydrogen and oxygen to produce electricity. With water and heat as the only byproducts, they are highly efficient and are used in a variety of applications, from vehicles to stationary power systems and combined heat and power plants. The third process is combustion. Hydrogen can be burned directly, much like natural gas in internal combustion engines or for industrial heating. This process generates mechanical power or thermal energy. While it is a more straightforward technology, it is generally less efficient than using a fuel cell and does not eliminate all emissions as it can produce nitrogen oxides. That's way the overall prospect of hydrogen energy. On the advantages side, hydrogen is incredibly versatile, can be a zero-emission fuel, and excellent for storing surplus renewable energy. On the disadvantages side, we face high cost of electrolysis equipment. The overall energy efficiency from production to end use can be low, and a major barrier is the current lack of a widespread hydrogen refueling and distribution infrastructure. And this will be the end of my topic. That's all. Thank you.
So, both solar thermochemical and hydrogen energy conversion systems show great promise in producing clean, sustainable energy. While challenges remain, their ability to store, transport, and convert energy efficiently makes them key technologies for a renewable energy future. So, these technologies both are promising solutions for in the future. So, this will be the end of our discussion, and I hope you have learned about the solar thermochemical energy conversion and hydrogen energy conversion system. Thank you for your time and attention.